topology, Moira's and Dennis's string topology. So, as heard during this conference, they have found quite a nice, rich structure in the homology of loop space of a manifold, oriented, say, d-dimensional manifold. In particular, there's an intersection product that lowers the total degree by the dimension of the manifold. And there's also a Lie algebra structure. And in fact, these structures exist on the chain level before passing to homology. So in thinking about these things, the goals that I had were to understand it in the following way. I wanted to understand, is there an actual structure on the loop space itself, topologically, that leads to this algebra, this algebraic structure on the homology or the chain level. And I'll say more about that in just a minute. I also want to relate it to other geometric structures on the loop space that have been studied recently, like symplectic floor homology, quantum homology, when the manifold has a symplectic structure. And finally, and this is something that I've been interested in a long time, is to understand what the existence of this intersection product says about duality phenomena in the loop space of a manifold. As you know, the intersection product on a closed compact manifold comes about because of Poincare duality. So the Chas-Sullivan product suggests that there's some kind of duality phenomenon. I wanted to understand that. So what do I mean by trying to find the underlying algebraic topological structure? For example, when you're in the space of based loops, so those loops that take the base point in the circle, which I'll call 1, to a fixed base point in the manifold, then the homology of that base loops is known for many, many years to be an algebra, to have a product, a Poincare product structure. And that's realized by an actual topological structure on the loop space itself, because you can take two loops and you get a new loop by just taking the circle, pinching it in that way, and doing one loop on top and one loop on the bottom, and you get the composition is the product of the loops. And the Chas-Sullivan product is compatible with this in an appropriate sense. Unfortunately, I missed Dennis's talk, so I'm not sure if he talked about that or not. Did you talk about that? No. Well, I'll mention a little bit about how it's compatible. And it's also compatible in an appropriate sense with the intersection pairing on the manifold itself. And so how can you, which of course does lower degree by d. So the question is, how can you topologically realize this algebra? So the trick, this is classical trick in differential topology, is to realize this intersection product using the Poincare construction. So let me just remind you about that and a couple of its properties. So suppose you have one manifold embedded in another, then there's a tone collapse map which takes the manifold and collapses it onto one-point compactification of a tubular neighborhood. And you can think of that, the tubular neighborhood, of course, is the same as the normal bundle of the embedding. And so you can think of that one-point compactification as the Tom space of that normal bundle over the embedded manifold. I'm going to use this kind of exponential notation to refer to Tom space of a bundle. And the map is just simply, if x is in the tubular neighborhood, tau of x is x, and if it's not in the tubular neighborhood, you just map it to the point at infinity. Classical construction. Now in cohomology, that classical construction leads to the so-called Schrick map that sends a cohomology class in the small manifold that's embedded. You use the Tom isomorphism, and that gives you a cohomology class in this Tom space, and it changes degree by the dimension, the fiber dimension of the bundle, which is the codimension. And then you just pull back via this Tom collapse map, and you get a map from the cohomology of n to the cohomology of m. And I guess it's called Schrick because it's a surprise that you go from the cohomology of the small manifold to the cohomology of the big manifold. You'd expect to go the other way. And in fact, when you compose this streak map with what you're used to doing, namely just pulling back a cohomology class or restricting it to the small manifold, what you get is multiplication by the Euler class. So this construction realizes topologically the Euler class. Now the example that I want to deal with is the diagonal embedding of a manifold. And here the tone collapse map would map this product manifold to the one-point compactification, or the Tom space of the normal bundle of the diagonal map. Now the normal bundle of the diagonal map is just the tangent bundle of the manifold. So you have a map for the product of manifolds to this Tom space of the tangent bundle. And in homology, you just calculate this in homology. You go to the homology of this Tom space, and then again apply the Tom isomorphism, and you're back in the homology of the manifold again, except the dimension shift because of the Tom isomorphism, and that's the intersection pairing. So in some sense, this Tom collapse map realizes the intersection pairing when you apply concurrent duality. Excuse me, when you apply the Tom isomorphism. Now I want to jazz this construction up a little bit. So so you don't, in jazz, you improvise on a basic theme, and you don't improvise unless the theme itself gets a little boring. Well, what's boring or not nice about this thing? What's not nice about it is that it takes the product of a manifold, and it doesn't lie in the manifold. It doesn't lie in the same space as you started with. So I want to jazz it up so that you get an actual product on some space that on a given single space, rather than the pairing from the manifold to a Tom space. Now the way you can jazz up the Tom Pontryagin construction is, suppose you have a bundle over your big manifold. Then you think of it as not just the embedding of the small manifold and the big manifold, but you think of it as embedding the bundle over the small manifold inside the bundle over the big manifold. And you look at that embedding of open manifolds. And you do the same kind of collapse map. Since they're open manifolds, you have to apply one-point compactification. And so the Tom Pontryagin map is a map from the Tom space of this original bundle over the big manifold to the Tom space of the restriction of that bundle to the small manifold, and then you have to add on the normal bundle of the original embedding. Sort of an exercise to just see what a tubular neighborhood of the bundle restricted to the small manifold is inside the bundle on the big manifold. And it looks like that. Now I want to jazz it up one step more. This also works when zeta is a virtual bundle. So by a virtual bundle, strictly speaking, I mean an element of K-theory, but I just mean a formal sum and difference of bundles. So you can have a formal difference of a bundle, so like minus an actual, so for example, zeta is minus an actual K-dimensional bundle. Now in K-theory, K-theory is a certain group completion of the monoid of all vector bundles. So the dimension takes values in all integers, so you have negative dimensional bundles. So here, the dimension of that bundle is formally minus k. And so you can talk about the Tom space. It's really a spectrum in the sense that Niels talked about a moment ago. But you just think about it as a Tom space. It's built up out of, you can embed your vector bundle in some trivial bundle and take the orthogonal complement. Your orthogonal complement has the property that when you add it to the original bundle, you get something trivial. That's how you build, that's how you talk about minus the bundle. Except the dimensions are formally shifted so that the Tom isomorphism would still shift the cohomology by the dimension of the bundle, which is now minus k. So the Tom isomorphism would go this way. So it's just a formal shifting of dimensions, like algebraic shifting of dimensions. And so, yeah, sorry.
This Tom spectrum is one space. It's supposed to just do you just take spectrums?
Yeah. Yeah. So one way, an easy example of a spectrum, in fact, the only kind of spectrum that I would deal with is if you is an object that may not be defined, but an appropriate suspension of it is a space, just a finite dimensional complex. So it's like a formal desuspension of a space. That's what I'll mean by a spectrum. So it just has the effect of being allowing to shift dimensions, shift degrees. So in particular, this bugger would have homology in negative dimensions. So anyway, that's just a formal dimension shift. But the topological construction works for these virtual bundles as well. And notice, so I'm going to take minus the tangent bundle on each of the manifolds. So what does that mean? It means embed your manifold into some Euclidean space and take the normal bundle, all of it, and then shift the dimensions appropriately. And do the topological construction, and you get a map from the Tom complex of this product, which is product of these Tom spaces, a Tom spectra. And you get a map to, well, when you restrict this product of minus the tangent bundle with itself to the diagonal, that's negative 2 times the tangent bundle. But the normal bundle was the tangent bundle itself, so you get negative 2 plus 1, you get negative the tangent bundle. So notice you actually get a multiplication. That's the improvising that this jazz is supposed to represent. So by jazzing up that topological Tom construction, you get a multiplication on this Tom space or Tom spectrum, and that's called a ring spectrum. It's a ring. It's a generalization of a topological ring. And notice that this ring structure has the property that when sorry. It's a good ring spectrum. It's associative, homotopy, commutative. It's an E-infinity ring spectrum, an E-infinity operator. And in particular, when you apply homology, see what that ring does in the homology, makes the homology into a ring. And you apply the Tom isomorphism, that gives you the intersection pair. So this Tom space, or Tom spectrum, strictly speaking, it has a product structure that topologically realizes the intersection pairing on a manifold. So the question is there such a thing for the loop space that realizes the Chas-Sullivan product? One more thing about this before I leave this example. There's an old theorem of Atiyah that says that if you take the Tom space of a normal bundle of an embedding, that's dual to the manifold itself. And it's a S dual, and Spanier-Whitehead dual. And that reflects Poincare duality. The Spanier-Whitehead dual of a manifold or of any space has the property that the homology of the dual is the cohomology of the thing you started with, and you have the duality structure. So you're seeing duality by doing this. And that, as I mentioned, that was one of my goals, is to try to see duality in the loop space. Because I should have said, you don't have Poincare duality in the usual sense of homology groups in the loop space. So what kind of duality phenomena are there? Well, one thing you can do is, in your loop space, that's an infinite dimensional manifold, you can map down to the manifold itself by evaluating a loop at the base point of the circle. And you can pull back the tangent bundle of the manifold, and that's a finite dimensional bundle over the loop space, an infinite dimensional manifold. And so the theorem that we can prove that I want to tell you a little bit about, a theorem that joint work with John Jones, is that if I pull back the virtual bundle minus the tangent bundle over the loop space, indeed you get a multiplication on that object, that Tom space. Not on the loop space itself, but on this Tom space of a bundle that makes it into a homotopy commutative ring spectrum. Well, so it makes it into a ring that's commutative. And it has the following properties. One is that the evaluation map from the loops to the manifold gives you a map of these Tom spaces. And that's a map of rings. That's one way of realizing the Chas-Sullivan theorem, or the property of their pairing, that their intersection product is compatible with the intersection product on the manifold itself. Now there's also a map from this Tom space to the actual base loop space of the manifold. that is a ring map, where the ring structure here is just the Pontryagin product that I mentioned before. And let me just tell you what this map does in homology to give you an idea. You take a homology class in here, and you apply the Thom isomorphism, so that's an element in dimension q plus d of the loop space, and you intersect it with the base loop space. The loop space of a manifold and the base loop space of a manifold are infinite dimensional manifolds, but the base loop is a finite codimension submanifold, codimension d, the dimension of the manifold. And so that shifts the degree by d. And that's what this ring map represents. And so again, these two together are the statement that the Chas-Sullivan pairing is compatible with both the intersection pairing in the manifold and with the classical Pontryagin product on the base loop space. And sure enough, I should have said this first probably, that this ring structure on this Thom space realizes the Chas-Sullivan pairing when you apply the Thom isomorphism. So remember, the Thom isomorphism in this case raises the dimension by d because the bundle is minus d dimensional. And this product, when you apply the Thom isomorphism, is exactly the string product that Mora and Dennis studied. So let me tell you a little bit about the construction of this product, and then talk about what I want to do with it. And this comes from this is really Mora and Dennis's idea that if you take a product of loops, evaluate each of them on the manifold, and restrict that. Think of that as a fiber bundle, and you restrict it to the diagonal, and look at the fiber product. So these are pairs of loops which have, when you evaluate at the base point, you get the same thing. That's what I mean by this notation here, this fiber product. Now, sure. Yeah, that's what I'm saying now. That's what I'm trying to describe now. So you have to describe it in a couple steps. There isn't a product on the loop space. There is no. What would be best if there was a map from LM cross LM to LM. There isn't such a map. But here there is a map, and this is what they pointed out in their paper, from this submanifold. From this fiber product to the loop space, there is a map. If you have a pair of loops that agree at a point, then you can just go around one loop and then the other, and you get a loop. The question is, how do you relate the homology of this to the homology of that? And that's what they talk about in their paper, and what I'd like to describe is how do you relate this. How do you do that on a topological level or a homotopy theoretic level? Now, if you look at this square, so the top horizontal lines, these are infinite dimensional manifolds, but the tubular neighborhood of this guy in here is just the inverse image of the tubular neighborhood of the diagonal map, which we understand pretty well. Namely, it's the normal bundle of the diagonal embedding, which is just the tangent bundle of the manifold. So that tells you that, well, that's a basic ingredient that allows you to do a Pontryagin collapse map. You just, as we did before, you take a point in here and you map it. It's no longer a one-point compactification of the tubular neighborhood, but it is the Thom space of the bundle. Same map. And you land in here. And now follow it by this map, and you end in the Thom space of the loop space. So this, to some extent, answers your question, I think, is that the product isn't a product in the loop space, but it takes a pair of loops, and it gives you something in the Thom space rather than the loop space itself. Now, to jazz this up a little bit so that you have a structure on the same space, you use the same kind of virtual bundle we did before over the manifold. And then the Pontryagin Thom map, or the Thom collapse map, is you look at the Thom space of this virtual bundle and you map it to the Thom space where you restrict this product bundle to this submanifold, and that's -2 times the tangent bundle. And you have to add the normal bundle of that embedding. And remember that normal bundle, the diagonal embedding, is the tangent bundle. And you end up with a map from the product of the Tom spaces of minus the tangent bundle to this Tom space of minus the tangent bundle here. And then you follow it by this map again, and you end up there. And this is the product structure. So it all comes about from these Tom Pontryagin maps, and that realizes the Tom collapse map. Now, let me just, I don't want to run over, so let me just say a couple things about how this extends and where it's going. It'll only take a moment or two. Sasha talked about his cactus operette today, this afternoon. So remember, a cactus is a well, that's what a cactus is. It's a cactus. Picture is a configuration of circles. And one extension is, for every point in the cactus, you get a where you have k components. You get a multiplication from k of these things to one of them. So it extends just the multiplication that I talked about before in a very particular way. The name for it is that it's an operad ring spectrum over this cactus operad. Now what this says is that for every element in the homology of these cacti, you get an operation. You get a map from the k-fold tensor product of the homology of the loop space to the homology. So this is what Voronov and Chas and Sullivan have. And what's the importance of that? Well, as Sasha pointed out this afternoon, CK is related to the operad, is homotopy equivalent to the operad of frame disk. Geometrically, I think the interest in that is that it's equivalent to the classifying space of a certain surface, this pair of pants with k legs. The legs each have spots on each of their cuffs, and these spots are preserved as a set. The waist is preserved point-wise. And as Sasha pointed out, this operator induces the BV structure in the homology. So that extra structure that was in the Chas-Sullivan paper also comes about topologically from this structure as well. And you can see that somehow these surfaces give the beginning of a field theory, or want to begin, which I might think of as a string homotopy theory, in that the coefficients are not in a Hilbert space or a vector space, but the coefficients are in one of these generalized topological rings, which have the property that when you apply homology or K-theory or homotopy groups or some other functor, you then get a field theory with coefficients in a vector space. So the way this generalizes that is if you have surfaces with K incoming boundaries and L outgoing boundaries, of course one knows how to glue those surfaces together. This is, strictly speaking, a two category in the sense that Niels was talking about a moment ago. And you have to do something a little bit weird. You have to take a collection of the Tom spaces of multiples of these normal bundles. So you just take the collection of all of them. And that's going to take the role of our vector space. So I need to tell you what tensor product is. Tensor product is you just take products of each of pairs of these things, and now the indexing set are pairs of positive integers rather than just positive integers. And each surface yields an operation from this collection of loops, these Tom spaces, to a k-fold collection to an L-fold collection, and it has a degree. And it's compatible under the gluing of surfaces, where if you glue a surface, the operations you get are composed. So it's a formal field theory in that sense. Now, why study this strange object? And let me just say, there's a sense in which this strange object wants to be the Atiyah dual of the loop space. So the Atiyah dual of a manifold, I mentioned this, is you take minus the tangent bundle, and you take the Tom space. So here you would want to take minus the tangent bundle of the loop space. Now, why is that related to what I've been saying? Well, the tangent space of a loop is a space of sections over a circle, over the circle that you get by pulling back the tangent bundle over the circle by the loop. Now, assume, just for ease of discussion, that the loop is contractible so that this bundle is trivial. So this is just the space of functions on the circle, tensor the tangent space at a point in the manifold. So if you complexify the tangent, you can think locally that the tangent bundle loop space looks like the tangent bundle of a manifold tensor Fourier series, Laurent series. Now, whenever you talk about tangent bundle or any vector bundle infinite dimensional, you better specify the structure group. Because there's Kuiper's theorem that says the general linear group of a Hilbert space is contractible. So if you're not careful, any vector bundle will be trivial when it's infinite dimensional, unless you specify the structure group. So what's happening here is that you're really thinking of taking the union of finite dimensional subbundles. You're thinking of your structure group as the limit of the unitary group. So you're studying finite dimensional guys in here. Well, what are those? Those are tangent bundles tensor Laurent polynomials of various dimensions. And those have S1 actions and a very rich structure. But non-equivariantly, they are just a certain multiple of the tangent bundle. So if you want to take the Tom space of minus the tangent bundle, what you really, from a homotopy point of view, is you're taking the Tom space of minus the tangent bundle of the manifold, tensor these various Laurent polynomial range. And that's exactly the object that we're seeing here. So in some sense, the Chas-Sullivan theory is pointing to an Atiyah-type duality on the Tom space of the loop space. Just to save time here, let me just say the relationship with, this is speculative, what I think the relationship is with things like quantum homology or symplectic field theory is, in that setting, when the manifold has a symplectic structure, the loop space ends up having structure. And the relevant structure is that the tangent bundle of the loop space has a polarization. And in that setting, the polarization, the structure group is a different structure group than what we were talking about before. You have a certain restricted general linear group that I won't go into, but it respects the polarization up to some finite dimensional ambiguity. And if you then apply a cohomology theory that respects this, so that's what physicists would call a semi-infinite homology theory, and you apply the same Chas-Sullivan technique, then I believe you're going to get Gromov-Witten theory. So somehow the difference between the string topology and the Gromov-Witten topology, I think, has to do with the structure group that you're putting on the tangent bundle of the loop space of the manifold. So, okay, thanks.